Good morning and welcome to the Seed Lecture. My name is Jim Collin. I'm the GI President, and it's a great pleasure for me to introduce Dr. Culligan, this year's recipient of the Seed Lecture. Dr. Culligan is the Matthew McCloskey Dean of Notre Dame's College of Engineering. She's internationally recognized for her expertise in water resources and geoenvironmental engineering, which focuses on the sustainable urban infrastructure, social networks, and the application of advanced measurements and sensing technologies to improve water, energy, and environmental management. Prior to joining Notre Dame, Dr. Culligan was the department chair and the Charlton Professor of Civil Engineering and Mechanics at Columbia University, where she also served as the founding Associate Director of Columbia's Data Science Institute and on the Executive Committee of the Earth Institute. Dr. Culligan is a Fellow of the American Society of Civil Engineers, a Fellow of the British Institute of Civil Engineers, and a Charter Engineer. She received her BS in Civil Engineering from the University of Leeds, England, and her Master's and PhDs in Soil Mechanics from Cambridge University. She has served on the Geo-Institute in multiple roles, including the GI's Board of Governors. Please help me in welcoming Dr. Culligan.
Well, thank you, Jim, for that kind introduction. I'm displaying the Seed Medal here. It was mailed to me. And I can say that it truly is an honor for me to be the recipient of the 2021 H. Bolton Seed Medal. I am grateful and humbled to be considered worthy of this honor, and I would like to extend my gratitude to the American Society of Civil Engineering and the Geo-Institute for selecting me this year, as well as IFCEE for hosting this event. I would also like to thank those who nominated me, including all of my colleagues in the Geo-Environmental Engineering Committee. I'm also very grateful to the very many people who supported my career along the way. I'm extremely fortunate that they are too numerous to name. However, there were three people that I would like to take a few minutes to recognize before we embark on the lecture. The first is Sarah Springman, a professor of civil engineering and only the second ever female to serve as rector of ETH Zurich. Sarah was a fellow PhD student in the soil mechanics group at the University of Cambridge and has been a lifelong inspiration and guide to me along my own career trajectory, showcasing accomplishments at all levels, from athletic to scientific to academic leadership, while also pushing for greater diversity in our geotechnical profession and the engineering profession at large. The second person I would like to recognize is Charles Ladd. Chuck volunteered to mentor me when I first began my faculty career in the US, and he remained my mentor until he passed away in 2014. Chuck was the person who introduced me to the ASCE and the Geo-Institute, encouraging me to get involved, and I did, starting with my attendance at Geo-Environment 2000 in New Orleans, which was actually held in 1995 in New Orleans during Mardi Gras. So it's memorable to many of us who attended for multiple reasons. Chuck's encouragement for my involvement in the GI led me to meeting many of my current geotechnical colleagues and friends, for which I remain eternally grateful. The third person I would like to recognize is Deborah Goodings, now a professor and associate dean for graduate programs at George Mason University. Deborah is another fellow PhD from the Cambridge University Soil Mechanics Group. When I started my own PhD, Deborah's thesis was held up as a North Star to aim for. It was concise, but because the work received the Outstanding Civilian Service Medal from the US Army Corps, I and my fellow PhD students were left in no doubt of the exceptional quality. Deborah is someone else who has been an inspiration and a mentor to me throughout my own career. Although a civil and geotechnical engineer by training, Deborah has not confined herself to addressing problems that are narrowly focused in these fields. Instead, she has conducted work that has wider application in, for example, material science, earth systems and environmental engineering, as well as the geosciences. Deborah has been lecturing on the proactive role that we engineers, including geotechnical engineers, need to take on in climate change impacts for well over a decade. Deborah's strive to put her talents to use in areas where geotechnical engineers can contribute to solving critical problems led me to also think of where I could contribute geotechnical and geoenvironmental knowledge to the critical issues of today. I believe that I would not have expanded my own areas of investigation and research if it were not for Deborah's role as an outstanding model in this area. So we can now start the slideshow. So today, I'm going to talk about quantifying the performance of urban green infrastructure in the context of the critical issue of urban water management. Before I start, I need to be able to advance my slides. Before I start, I wanted to say just a few words about Professor Harry Seed. Unlike many prior recipients of the Seed Medal, I did not have the privilege to meet Professor Seed. However, he and I share a few things in common. As you heard, I received my engineering education in the UK, as did Harry Seed. We both received our undergraduate and our PhD universities in England. We then also both found ourselves on the faculty of US universities. Among Professor Seed's many accomplishments, he is known to be someone who brought colleagues together from different areas of geotechnical engineering to build an outstanding program at Berkeley. He also established the field of geotechnical earthquake engineering, and through teaching, research, and practice, was influential in improving the safety and performance of critical infrastructure. Dr. Seed also chaired the 11th International Conference on Soil Mechanics and Foundation Engineering, which was held in San Francisco in 1985. I was a first-year PhD student at the time, and many senior members of the Cambridge University Soil Mechanics Group attended the conference, including my own PhD advisor, Professor Andrew Schofield. These senior members came back to Cambridge excited about the events. Dr. Jimmy James claimed that he had been allowed to pilot a plane that flew under the Golden Gate Bridge. None of us were sure if that was part of the program or not. However, we PhD students pored over the conference proceedings for knowledge and inspiration. I note here that one of the sessions was on hydrology and geotechnics and urban problems. I, at the time, was working on contaminant transport in soils, so was very much interested in the hydrology aspects. Today, several decades later, I find myself working on urban hydrology issues, and I'm going to come back to that at the end of my talk. Here is an overview of what I would like to present for the remainder of this lecture. I am going to first define the urban hydrology problem I have been very much involved in for the past decade or so. I am then going to explain why many urban areas are turning to green infrastructure as a solution to this problem. I will then describe work to quantify the performance of green infrastructure through multiple approaches, from field measurements to system-level performance. Next, I will introduce some work on quantifying the social benefits of green infrastructure, and then I'll move to make some closing remarks. Before I start, I would like to acknowledge all of the students, collaborators, and sponsors of this work up front. Close to 20 students, and I have listed their names here. From undergraduates to PhDs have contributed to this work over the last decade. The work has been in collaboration with multiple colleagues. Apologies. From geosyntech, as well as academics from areas spanning climate science to anthropology. And we have been lucky to have been sponsored by multiple government agencies, including the CMMI and CBET divisions of the National Science Foundation, as well as industry. So what is the urban hydrology related problem that I am going to be discussing? In this slide, we are looking at a cartoon in the bottom right-hand corner showing the hydrological cycle in a pre-development landscape illustrated here. And we note that 40% of precipitation that falls on this landscape is returned to the atmosphere by evapotranspiration. 50% is infiltrated below the subsurface and recharges shallow and deep aquifers, and 10% runs off the ground surface. By contrast, in an urban landscape, as illustrated here, only 30% of precipitation that falls returns to the atmosphere as evapotranspiration due to widespread imperviousness. Only 15% infiltrates the subsurface, recharging shallow and deep aquifers, and 50% becomes runoff, generating a stormwater disposal problem. In other words, an urban hydrology problem. In developed nations like the US, the stormwater is collected in underground pipe network systems. In older cities, including New York, the pipes are single pipe systems, as illustrated at the top here, that collect both sanitary sewage from the urban buildings and the stormwater runoff in a single pipe and deliver it to the local wastewater treatment plant. These legacy double pipes, also known as combined sewer systems, were not built for the capacity of combined sewage and stormwater they have to deal with today. And when their original capacity is exceeded, they eject a combination of sewage and stormwater into local water bodies. This event is known as a combined sewer overflow, and there's an illustration of a combined sewer overflow in the top right-hand picture. In New York, there are over 400 combined sewer overflow outlets where a combination of sewage, sanitary sewage, and stormwater is ejected into local water bodies. And combined sewer advisories are a frequent occurrence. Newer cities have double pipe systems, as illustrated here, which often discharges the stormwater into local water bodies without treatment. Combined sewer and stormwater overflows are one of the leading causes of coastal and inland water degradation in the US today, with the EPA calling this one of the most significant environmental problems of our time. In addition to water pollution, as illustrated in this photograph here, stormwater runoff issues also include local flooding that can damage underground infrastructure and severely disrupt city life. In developing nations, underground pipe network systems are absent, so the problems caused by stormwater runoff are an order of magnitude worse. One solution to the stormwater management problem that has gained popularity in the last decade or so is urban green infrastructure. Can we restore the pre-development hydrological cycle in our cities by increasing vegetation in our urban landscape? Increased vegetation will allow precipitation to be infiltrated where it falls and prevent the runoff that leads to urban stormwater management issues. New York City where the work I am going to describe took place, has embarked on a very aggressive green infrastructure program to deal with urban stormwater management issues, and in particular, the pollution caused by combined sewer overflows. To date, the city has invested $1 billion in over 11,000 green infrastructure assets with a goal of reducing combined sewer overflow and the attendant contamination by 1.6 billion gallons a year. Although I'm going to be focusing on green infrastructure for urban stormwater management in this talk, there is also increasing interest in green infrastructure programs for climate resiliency. This is particularly in the face of increased wet weather flow under climate projections and hotter urban environments, in addition to the potential for green infrastructure to lower building energy demands and reduce water energy costs, and at a larger scale, possibly contribute to coastal resiliency in the face of rising sea levels. I have an illustration here of some example green infrastructure strategies. I am going to talk mainly about green roofs, illustrated in the top left-hand picture here. However, there are also green streets, tree and vine canopies, and bioswales and rain gardens. My collaborators and I have studied the performance of all of these interventions, and results can be found in some of our papers if this is of interest. Our most recent papers have actually involved the right-of-way bioswales illustrated on the right-hand side of this slide, as this is the green infrastructure intervention that is most aggressively being pursued in New York City. So, on to discussing the quantification of green infrastructure performance. I'm going to be presenting results and findings that are relevant to extensive green roofs, as illustrated here. Extensive green roofs are lightweight and can be retrofit to existing building stock, so are most relevant for greening established dense urban environments like New York City. In New York City, about 40% of the hardscape is rooftop area. So green roofs also offer a considerable advantage when it comes to the land area that is available for greening. Of course, many green rooftops are owned by private, many green rooftops are in private ownership, so there is an interesting ongoing discussion about the use of private space for public good, which I will not get into in this talk, but it is documented in some of our publications. So this is a cross-section through an extensive green roof. Those of you who are familiar with geotechnical infiltration barriers, including landfill caps and other waste containment barriers, will recognize some of the layers. The base of the green roof, which comes into contact with the building's membrane, is comprised of a geosynthetic drainage material that transports water that infiltrates through the above layers horizontally towards the roof's drainage system. Above that base drainage layer is a retention fleece to hold moisture in the green roof's growing medium. The green roof's growing medium is an engineered lightweight soil that comprises of organic and inorganic components. The growing medium supports the vegetation, which is the top layer of the roof. This vegetation is generally sedum, a desert succulent that can support the harsh temperature swings on urban rooftops. There are three common types of extensive green roofs, and they are illustrated here. I'm going to focus on the bottom type, which is a vegetated mat system. The roof layers that were shown in the previous slide in vegetated mat systems are actually assembled off-site and rolled into something that looks like a carpet, which is then installed on the rooftop. Just briefly, my collaborators and I have actually studied the performance of all of these common extensive green roof types, including the complete type, where the roof layers are constructed on the roof itself, and the tray system, where the roof layers are constructed in trays that are built to the rooftop, as well as the vegetated mat that we'll go into a little bit more detail in the next few slides. So here is a simplified hydrograph showing a rainfall event and the runoff from a green roof. This is the rainfall event shown here, and the shaded portion is the hydrograph illustrating the runoff from the green roof. The rainfall is retained by the green roof, so the area under the shaded portion is lower than the area under the rainfall hydrograph. So runoff is both delayed and reduced. To the right is a hydrograph obtained from field measurements. The blue line is the rainfall. The black line is runoff from a non-vegetated roof, and the green is runoff from the green roof. So again, the green roof is able to both delay the time of runoff and retain the amount of rainfall that falls on the roof. So moving on to quantifying green roof performance using field measurements. Here is a simple water balance for a green roof. Precipitation that falls on the roof can be returned to the atmosphere as evapotranspiration. And this is one of the hardest components of the water balance to quantify. Some precipitation also turns into surface runoff, some into storage in the green roof growing medium, and some infiltrates through all of the layers of the green roof to the base and exits the roof as base runoff. We have been monitoring green roofs for close to a decade. We have met stations on all of our green roofs to measure precipitation and other climate variables that are important to green roof performance. We measure the storage in the green roof through the use of moisture probes, and we measure the runoff, both the surface runoff and the base runoff, using weirs we have developed and installed at drainage outlets on the roofs. Data loggers on the roof collect data in real time, and we use wireless or other protocols to store data in secure cloud systems. At one time, we had 6 active green roof monitoring stations. We're now down to about 3, where we have almost continuous data collection for about 84 months. Here, I am showing some field measurements collected from a vegetated mat system illustrated in the photograph, located on a Columbia University residential building at West 118th Street. We refer to this roof as W118. This plot shows runoff normalized per roof area on the vertical axis and normalized rainfall on the horizontal axis on a log scale. The solid black line represents a situation where rainfall is equivalent to runoff. As you see, most points lie below the solid line. So runoff is less than rainfall, meaning that the roof is doing its retention job. There is no runoff if you look at the smaller rainfall events on this plot, if the rainfall is only a few millimeters. Under these circumstances, the green roof is retaining all rainfall and not generating any stormwater runoff. If we fit, however, as rainfall increases, runoff increases, which is intuitive. If we fit a quadratic, which is illustrated by this baseline here, through the field measurement data, we can use it to predict green roof runoff based only on rainfall data with an accuracy of about 80%. However, we see for some rainfall depths, we can look at this example here, we have a range of runoff observations. So rainfall alone is not sufficient to predict runoff. If we plot the residuals between the quadratic predictive line and runoff, observed runoff, which is shown here, we'll see that the quadratic predictive line underestimates runoff in winter and overestimates runoff during summer months. So some variability can be explained by the seasonal behavior of the green roof. Evapotranspiration will change with seasons, and as this is a living system, the contribution of the vegetation to the green roof performance and many green infrastructure performance will also vary seasonally. We have actually been able to come up with some more sophisticated empirical or data-driven models, as we like to call them these days, for green roof performance that are based on multiple years of our field measurements. These more sophisticated models capture variability in rooftop runoff for the same rainfall depth. And this dark line here shows our model predictions on the same plot of normalized runoff versus log normalized rain depth, showing that our model is able to encompass most of the observations that we made. Our more sophisticated models take into account seasonal variability in air temperature and solar radiation, and we use Julian days, referred to as JD, as a surrogate for this. However, we can also use some of the measurements that we make on the MET station at the roof. And they also take into account the antecedent dry weather period, referred to here as ADWP. That's the dry weather period between rainfall events. Specifically, if the roof has been dry for 3 days, it will capture more rainfall than if it was wet the day before. So even for the same season, we'll see variation in roof runoff depending on the frequency of the rainfall events. This plot here shows predicted runoff by one of our more sophisticated models. You'll see it's a function of Julian day on the horizontal axis, as well as rainfall depth, which is illustrated by the different shaded bars here. We can see seasonality, both in roof behavior, less runoff in the middle of the year than in the winter period. We can also see changes in runoff as a function of rainfall depth. Overall, we have been very successful using our multiple years of field measurements to understand the complexity of green infrastructure behavior in an urban environment. So in a real world setting and not in the lab. And then using the field monitoring data, our field measurements, to build models that have very good predictive capacity. However, this requires multiple years of data and a lot of rooftop instrumentation. So we have also looked at where we can use modeling approaches to quantify green infrastructure behavior instead. I'm going to present some of our modeling results using HYDROS-1D, which will be familiar to those of you who work in unsaturated flow. HYDROS-1D solves Darcy's equation, illustrated here, for unsaturated flow. But in order to solve this equation, it's necessary to know the relationship between unsaturated conductivity and soil saturation level. We used measured pressure plate testing in the lab to get this relationship for the green roof media, as illustrated here. We were then able to predict individual storm events using rainfall as the upper boundary input to a HYDROS model that was set up to include the green roof layers. We assumed free drainage at the bottom layer of the green roof. Here, I show some example runoff predictions, again for the W118 roof. And as you can see, comparing the modeled runoff, which is the red line here, to the observed runoff, which is shaded in gray, for these three different storm events. One is a small, medium, and then large storm event. The predictions are quite reasonable in capturing runoff variability during individual storms. It's possible to run the HYDRIS model for multiple years, as long as you have an initial condition, which would be the moisture content in the roof at the start of your modeling, and the input conditions, which would be the rainfall events themselves. We ran HYDRIS for a year of rainfall events and compared the model output to our field measurements. These dots illustrate the HYDRIS model output, and the straight line would be a perfect one-to-one correlation between model output and our observations. We found that HYDRIS overestimates runoff, which is shown on the left-hand graph, and either underestimates, shown here, or overestimates peak runoff depending on the storm size. We found that HYDRIS actually does a very good job, and I haven't illustrated this here though, at predicting the time for peak runoff. We've actually explored the use of multiple models to predict green roof runoff. In addition to HYDRIS, we've looked at how HELP, hydrological evaluation of landfall performance, which some of you may be familiar with, how good HELP has been in predicting green roof runoff. We've also looked at SWIM, Stormwater Management Model, which was specifically designed for modeling stormwater runoff, as well as a curve number approach. We found that the main barrier to accurate predictions from any of these models is describing the evapotranspiration behavior of green roofs or any other green infrastructure system, and the unsaturated flow dynamics. In many cases, these models actually use empirical relationships to describe evapotranspiration or unsaturated flow dynamics. And it's actually hard to parameterize these empirical relationships. And even if it's possible to parameterize them, as we did with our use of HYDRIS by using pressure plate testing in the lab, these parameterizations often don't capture the full complexity of these complicated processes. Overall, and probably not surprisingly, we have found that the models that we have developed using the multiple years of field measurements are more accurate than the common process-based models used to quantify green roof performance. We are also finding the same when it comes to right-of-way bioswale performance. So this finding is not exclusive to green roof performance. We have explored models that are based on minimal field measurements. This is a combination of using field measurements and process-based models to quantify green roof performance. It has the advantage of capturing some of the complexity of green roof performance through real measurements made on a green roof, but not requiring the multiple type of measurements that we use to develop some of our empirical models to capture green roof performance. So it's a hybrid of extensive field monitoring and process-based modeling. One such model that we've developed is called SWAM, the Soil Water Apportioning Method. SWAM uses rainfall and soil moisture readings as input. The basic premise is a simple bucket model that uses soil moisture readings to determine rooftop evaporation when it is not raining. So the decrease in soil moisture in between wet weather periods is an indication of how the green roof is returning water to the atmosphere. It then switches to using soil moisture readings to determine green roof water storage when it is raining. So how the green roof layers are absorbing rainfall during a wet weather event. When the green roof storage reaches capacity, it predicts runoff based on excess rainfall. Here are some results that are generated by SWAM for different time steps. The model can be run at any time step, depending on the time step that you're gathering your soil moisture readings. SWAM does a reasonable job predicting runoff. As shown here, these are predicted versus observed runoffs for multiple years of events on the 118 roof. And these are for different time steps at the model. And a better job than most process-based models predicting ET, which is shown on the right-hand side here. But there is still room for improvement when it comes to the ET predictions. If we just focus on the efficacy of SWAM for predicting green roof runoff, we find that using moisture and rainfall to predict runoff is actually accurate for the majority of storm conditions in New York City. And here's a plot of errors, SWAM errors as a function of rainfall depth, normalized rainfall depth, and rainfall intensity. And most rainfall events in New York City would fall in this area here. However, when it comes to predicting more intense storms with greater rain depths or higher rainfall intensity, SWAM has greater errors. Because we're expecting more intense storms under climate change predictions, there is a question about how accurate this method might be under a hydrological regime where we have larger rain depths and greater intensities. We've also developed models for runoff for bioswales that are based on rainfall and soil moisture data. We actually think that there is promise for using this approach to quantify the performance of very many green infrastructure interventions. At scale, the issue becomes one of data collection. So we're now looking at developing low-cost, low-power sensors with colleagues in electrical engineering and the use of LoRa platforms for data capture. We are currently testing this system on the Columbia University campus. The advantage of SWAM and the use of minimal measurements is that we will be able to gain a greater understanding of different green infrastructure intervention performances in different settings over a wider range of field sites than we are able to with the intense monitoring that we have been conducting on the couple of field sites that we've monitored for close to 84 months now. My research group and others have expended a lot of time and effort quantifying the performance of individual green infrastructure components. And I still think there remains a gap or an open question about the performance of thousands of individual green infrastructure components as a system. The fundamental question is, are green infrastructure programs in fact meeting their goal in reducing the water pollution that is caused by stormwater runoff? So I'd now like to move on to how we've been looking at quantifying system level performance of green infrastructure. To do so, we have been using enterococci samples collected at 50 water sites across New York City over a period of 7 years. This is a data set that is being collected by citizen scientists that comprises of thousands of E&T concentration measurements. Here I've illustrated the E&T collection sites with respect to New York City water bodies. Enterococcus is a gut and bowel bacteria, so is a surrogate for pollution that is caused by combined sewer overflow. Here, I show box plots on a graph that we created using the citizen science data set. The vertical axis here is the bacterial concentration, so the fecal indicator bacterial concentration. And the horizontal axis represents the 50 collection sites. I've left off their names for the sake of not making this graph too busy, organized from sites where we've seen the highest bacterial concentration to sites where we've seen the lowest bacterial concentration. The blue boxes represent box plots for concentration measurements that were taken within 6 hours of a rainfall event at the collection site. And the red box are box plots of the data, the concentration data that were measured when there was no rainfall within 6 hours. You know, as is obvious, the blue boxes are higher than the red boxes. And in most cases, there is a statistically significant difference between the measurements that were made at the sampling sites within 6 hours of rainfall and the measurements that were made at the sampling sites when there was no rainfall within 6 hours. So we've used this box plot and other analysis to confirm that elevated enterococci concentrations are indicative of combined sewer overflow. So this is a good surrogate for water pollution caused by CSO events. I put here on this graph a horizontal red dotted line. This represents the EPA cutoff for swimmability of water, which is equivalent to 100 mpn per 100 milliliters of water. Below the red line, the water contamination, or the concentration of Enterococcus in the water, is low enough that one can swim. Above the red line, the water is too contaminated for direct contact. We use the runoff coefficient as a surrogate for urban greening. The runoff coefficient is the fraction of rainfall that turns into stormwater runoff. So higher values mean greater stormwater runoff. The runoff coefficient varies from 0, no runoff, to 1, 100% runoff. We based our runoff coefficient on land use cover obtained from multiple sources in collaboration with colleagues at IFCEE and Columbia University. These multiple sources included GIS databases and aerial photography. We found 100 different land use covers for New York City, but as shown on this graph here, 9 were dominant. We used our land cover data to obtain the runoff coefficient of land areas in New York City that were adjacent to combined sewer overflows. I illustrate here a map showing high runoff coefficients illustrated in red in lower Manhattan and lower runoff coefficients illustrated in green in areas of Queens and the Bronx. We divided our runoff water coefficients into combined sewer overflow sheds and associated each of those combined sewer overflow sheds with the sampling sites where the citizens were collecting information on bacterial contamination indicative of a combined sewer overflow event. When we looked at the bacterial concentrations in local waterways 6 hours or less after rainfall events occurred, shown on the vertical axis here, versus the runoff coefficient shown on the horizontal axis here, we found 2 data sets based on a cluster analysis. One data set, shown as the red dots on this graph here, indicates that bacterial concentrations after rainfall and combined sewer overflow are lower in waterways next to land areas where there is less runoff. So we see a clear trend between water contamination and the runoff coefficient, with higher runoff coefficients leading to more water contamination after a combined sewer overflow event. The other data set in green, however, shows no trend with runoff coefficient. So the runoff coefficient, which is linked to the amount of greenery, including green infrastructure, that has been inserted into the urban fabric, is not influencing contamination caused by a combined sewer overflow event. It turns out that the red data, shown as dots on this map here, are associated with slower moving water bodies in New York City, including canals, creeks, and rivers, while the green data, also illustrated on this map, are associated with some of the faster moving water bodies in New York City, including the Hudson River and the East River, where we see significant current speeds. We used a random forest machine learning algorithm to predict swimmability at the 50 water sampling sites using the 7-year data set of bacterial measurements. Some of the data sets we used to calibrate the model while as a training data set, while the others was used as a predictor so that we could understand the accuracy of our model. We found that the runoff coefficient, so urban greening, did make a difference. It's actually ranked 4th out of the top 5 predictors of our model, but it only made a difference in cases where combined sewer overflow was injected into the slower moving water bodies. The top predictor was current or water body speed, with lower speeds being associated with less swimmable water bodies after a rainfall event. The area of the land that was draining into the water body during a combined sewer overflow was also a predictor. More land meant less swimmable. A larger land area meant less swimmable. The population of the area and also the depth of rainfall in the prior 18 hours were also good predictors of swimmability. This model is actually 84% accurate at predicting swimmability of water bodies after rainfall based on the 50 collection site data and the 7 years of data. So this actually begs a question about what are the things we need to measure and understand if we want to consider system level performance of green infrastructure or any infrastructure of multiple components. Specifically, how important is it for us to accurately quantify the performance of the individual components themselves, as my group and our collaborators and many other research groups have done? I actually want to finish with a few slides on quantifying the social benefits of green infrastructure. As geotechnical engineers, we normally don't get involved in trying to quantify the social impacts of our work. However, I believe that we ought to, because our role as engineers is to help build a better world for all. So here's a lady in Queens. She's not happy that a green infrastructure intervention came her way. This is a right-of-way bioswale. She's concerned that this right-of-way bioswale attracts trash. It hinders street parking. It's a haven for urban wildlife like rats. And it has been vandalized. You'll see that the vegetation is largely missing. And all of these points and concerns are very valid. We've used several survey techniques, both qualitative and quantitative, to understand how and why people value urban greening and green infrastructure. And we have found that cultural and social benefits are ranked more highly than stormwater management and other environmental benefits, with the ranking shown here on the vertical axis. And these are box plots showing the results of our surveys for different categories of green infrastructure, including non-vegetated green infrastructure interventions such as rain barrels. Where we have gone deeper into relationships between urban greening and well-being, we have actually found that feeling connected to nature in an urban environment is important to people's self-reported levels of well-being and happiness. And when we've looked at the elements that people quote in determining their relationship to connectedness to nature, I know this slide is hard to read, so I apologize. Trees and vegetation are a big part of that. So it's certainly true that adding vegetation to our urban landscapes might well improve people's sense of well-being and add significant societal benefit. However, we've also found in our qualitative and quantitative surveys that the size of green space that people associated with improved happiness and well-being is much larger than the size of the green infrastructure interventions that many of our cities are introducing into their urban landscapes in order to deal with stormwater management issues. So it's unclear how many of our current green infrastructure designs are at an optimal scale for reaping the maximum societal benefits. So there is certainly room for improvement of green infrastructure performance in this particular category. So my closing remarks. And I want to bring them back to Professor Seed. Professor Seed's approach of building collaborations across areas in order to advance new fields remains extremely important, if not essential, as we take on new challenges as a geotechnical and geo-environmental engineering discipline. As Professor Seed emphasized societal benefits in his work, and in his case, that was based on improving the safety of critical infrastructure, we too need to emphasize societal benefits in our work. And maybe that means adding new measurement tools and new approaches and new collaborations to our 21st century belt of tools. We as geotechnical engineers still have important roles to play in addressing hydrology-related urban problems. It's tying it back to the 1985 conference that Professor Seed chaired. That includes understanding the role of green infrastructure in addressing urban stormwater management challenges, which are only predicted to get worse under climate change. And that's most especially in developing countries. I think we have a lot of expertise to add when it comes to field measurements, as I hope I've illustrated, when it comes to model development and validation, and when it comes to advancing system-based approaches for quantifying the performance of systems that comprise multiple components. So that concludes my presentation. Again, I'm extremely honored to be the recipient of the 2021 H. Bolton Seed Medal. It's an honor that I was not anticipating and an honor for which I'm extremely grateful. I would like to thank the Geo-Institute for bestowing this honor upon me. I would like to thank IFCEE for hosting this talk. And I would also like to thank my very many mentors, collaborators, sponsors, and students who have supported me throughout my career. And with that, I conclude.
Trish, I just want to say thank you for the lecture today. It was fantastic. Couple of comments from me. It really spoke to me as an environmental science minor all those years ago. It's very exciting to me when I hear one of our members or somebody from the geotechnical community make these connections with this adjacent discipline that doesn't always happen. So I want to thank you for doing that today. And I said it 20 times. I love that Notre Dame wall art behind you. And even though I was raised to despise Notre Dame and those gold helmets, I can't help but love it. But this was fantastic. And thanks again for doing this. And we're very fortunate to have heard this morning. It's really enjoyable. A couple of quick messages before we wrap up here. The Gerwick lecture, one of DFI's award lectures, will be in this very room in about 45 minutes at 10 a.m. Central Time for those of you who are in person. For those of you online, you can watch it in the conference platform or live streamed on our YouTube channel. And this afternoon at 3:30 Central Time, the Terzaghi lecture, the 57th, Terzaghi lecture delivered by Greg Bacher of the University of Maryland. Same thing. It will be in this room. You can find it in the conference platform. You can find it on our YouTube channel. You will all have noticed my wardrobe change into another piece of GI apparel. There is really no additional significance to this one other than I really like it and it looks good. We'll see what I have up my sleeve for this afternoon. So thanks again to Trish, and thanks again for all of you for sharing this lecture with the world this morning, and have a great day at IFCEE.
So we live out in our old van, travel